Hi everyone, I'm Jingwen, a PhD student from the Hybrid Body Lab at Cornell University. Today, I will present our work titled SkinPaper, Exploring Opportunities for Woven Paper as a Wearable Material for On-Skin Interactions. Paper is a ubiquitous material widely used in everyday life. The accessibility and familiarity of paper make it a material commonly used for beginner-friendly crafting and design. While paper circuitry has been explored in HCI research to enable interactions on paper, it has been mainly used for creating desktop or handheld objects. We had a question: could paper be used as a wearable material? Paper has been used to make garments for centuries. In fact, traditional Japanese kozo washi paper can be shredded into thin strips and woven into textiles. While washi paper is durable when wet and can be washed like clothing, it needs improved hydrophobicity for on-skin wear. Previous research has explored using organosolines to make paper omniphobic, but this requires professional chemistry equipment and handling hazardous waste. In SkinPaper, we identified an accessible method using off-the-shelf silicone-based sprays to treat the paper hydrophobic. For an on-skin context, we adopt techniques from paper weaving and basketry weaving, which can render both 2D and 3D structures for curved body locations. Our related work are from three topics explored in HCI community. First is paper circuitry, which has been widely explored through crafting conductors onto paper substrates and combining origami and kirigami to create paper electronic components. The second is woven interfaces. In the HCI community, textile weaving has been most widely investigated to create sensing and actuating soft interfaces. The third is on-skin interface fabrication. Advanced material science research has explored various materials to create thin and flexible circuitry for on-skin interactions, including PDMS, hydrogels, or tattoo decal paper. We present SkinPaper, a fabrication approach using silicone-treated washi paper to weave lightweight and easy-to-fabricate on-skin interactions. We adopt techniques from paper weaving and basketry weaving to create paper-woven structures that can conform to the body. Here, I will introduce you the SkinPaper design space. We adopted a research-through design method to explore the materiality of paper-woven on-skin interfaces. The Twofold design space consists of paper primitive elements and woven structuring techniques. The primitive paper architecture consists of 4 layers. We use traditional washi paper as a base material. The design layer can be used for aesthetic purposes as well as functional purposes. For the hydrophobic layer, we identified an accessible method using non-hazardous off-the-shelf silicone-based spray. The interaction layer enables the application of conductive and interactive materials to create circuitry. To afford weaving, the paper needs to be pre-processed into weavable elements, such as strips or cut slits. Users can choose the size and shape of the paper primitives according to their skill level and desired fidelity of the prototype. Here's the fabrication process. First, customize the design layer by inkjet printing, stenciling, or hand-applying watercolor paint. Second, apply the off-the-shelf silicone-based spray onto washi paper. Third, apply interaction layer by applying metal leaves using stencils, print with conductive ink, or adhering conductive fabric tapes. In the last step, paper sheets will be cut into weavable paper primitives according to the design. This step can take place during the weaving process for improvised adjustments. After achieving weavable paper primitives, it's time to weave. We synthesized the woven paper structure design space with suitable body locations. 2D pattern includes single-layer and double-layer patterns for cylindrical or planar body locations. These 3 studies show the interaction that can be achieved with 2D patterns. They are plain weave touch sensing matrix, double weave thermochromic patch, and 12 weave NFC tag with cut slits. Foldable and protruded 2.5D textures are for easy-to-reach or ice-free interactions. These 3 case studies show the interaction that can be achieved with 2.5D textures. They are behind-the-ear fuzzy weave touch input, collapsible texture as pressure input, and protruded dome texture for LED diffusion. 3D structures including cubic, concave, and tubular for protruded or joint body locations, such as knee, neck, and shoulders. These 2 case studies show the interaction that can be achieved with 3D structures. They are 3D heating patch for knees and tubular finger touch sensing slider. SkinPaper design space allows for low floors to support a beginner-friendly fabrication, high ceilings to enable sophisticated projects, and wide walls to support versatile designs, as illustrated in this figure. Here, I will introduce the evaluation of SkinPaper. To understand the material, we conducted hydrophobicity, bending rigidity, and tensile strength characterization. To understand the variability factors, we recruited 10 participants to wear SkinPaper sample for 8 hours while continue their regular daily activities. The study demonstrated the mechanical durability, electrical functionality, and comfort of SkinPaper devices. To discover how individuals with diverse weaving experiences adapt this new fabrication approach to their practices, we conducted a workshop study inviting 4 participants with weaving experience ranging from 1 year to 40 years. Their pseudonyms are Luna, Iris, Ruth, and Scarlett. Each study includes a brainstorm session, a craft session followed with a post-study semi-structured interview. Luna created a shoulder piece at Easy's pen with controlled heating. Ruth created a light-up bracelet using 2 unique basketry weaving binding techniques. Iris' project is a neck and shoulder harness that senses touch on the neck. Scarlett designed a headpiece that senses head movements. Participants at the workshop were given a fixed time frame to prototype a woven structure using the prepared paper primitives. Despite being a new material for some, the familiarity of paper allowed all the participants to complete multiple iterations, demonstrating the accessible nature of the fabrication approach. During the workshop, participants adjusted the properties of paper to create versatile and expressive interfaces. All designs went through multiple iterations, and on-body weaving allowed for improvised adjustments. As the outcome of the research through design process, SkinPaper affords a new user-friendly design strategy for making on-skin interfaces through the Twofold design space for paper weaving that leverages versatile materiality, on-the-fly adjustments, and on-body fabrication as discovered in our case study and workshop study. During our studies, we observed that after being peeled off from the user's skin, the woven piece can be reused. This enables reusability towards sustainable on-skin fabrication. Compared to textile weaving, the other 2 weaving types have less documentation yet offer unique design opportunities. We see an opportunity to expand the weaving circuitry spectrum in HCI research to incorporate more multi-material weaving practice. In the future, we could utilize flexible PCB to be interwoven with paper primitives to realize a fully integrated woven paper circuitry. In conclusion, we present SkinPaper, a fabrication approach using silicone-treated washi paper to weave lightweight and easy-to-fabricate on-skin interactions. Through SkinPaper, we envision expanding on-skin interface fabrication to broader audiences. We thank everyone from Hybrid Body Lab for their support. We want to thank all the user study participants for their engagement and all the reviewers for their time and feedback. The project was supported by the National Science Foundation. Thank you for listening.